Hi everybody. Today we're going to be talking about magnetic fields and magnetic forces as they relate to the right-hand rule, as well as cover an MCAT-like question on these concepts. So the first thing we're going to do is talk about magnetic fields, which are denoted by the letter B. Magnetic fields are vector quantities, meaning they have a magnitude or a strength and a direction. So magnetic fields are produced by moving electric charges and as such are defined as the force on a moving charge, which is why for the equation for magnetic field you'll see it is equal to force divided by Q times V, which is the charge as it is moving with a velocity V. So one magnetic field that you may encounter in a few problems is the magnetic field of the Earth, which has a value of 5 times 10 to the negative 5 T for Tesla, which is the unit for magnetic field. So Earth produces its own magnetic field that is used for navigation and also shields us from solar wind, which is the stream of charged particles released from the upper atmosphere of the sun. So next we're going to talk about magnetic force, which is denoted by the letter F. So the force is derived from the product of Q and V, which is the moving charge, and B, the magnetic field that is perpendicular to QV. So the equation for force from magnetic field on a moving charge is equal to Q times V times B times sine of theta, which is the angle or the direction of the moving charge. So one note here is the force that we're solving for with this equation is actually perpendicular to the 2D plane of B and V, because as we said, the moving charge and magnetic field are perpendicular to each other. So we can imagine this 3D space by using the right-hand rule, which we're going to cover now. So the right-hand rule is, by using your right hand, you can imagine the 3D space of magnetic field, magnetic force, and the moving charge, which are all vector quantities. So here on the left side, we provided a plane of x, y, and z, where x and y produce a two-dimensional plane, and then by adding the quantity z, we're making it three-dimensional. So you can see how these quantities make sort of a cube, which is three-dimensional. So then as we apply it to our right hand, if we have our right hand on our palms, with our palm side showing, we can see how the magnetic field is extending out from our fingers, and then the velocity of the charged particle is perpendicular to that magnetic field and extends out from the thumb side. And then so this force, depending on whether the charged particle is negatively or positively charged, will determine whether the force will extend out from the palm side or from the back of the hand. So if the charged particle is positively charged, the force will extend straight out from the palm of the hand, and then whereas if it's negatively charged, it'll extend out from the back. And this information is written here below as well. So now we're going to provide a few problems where you can pause the video and solve for these. We're looking to identify where the magnetic force, what direction that will be going. So in this first problem here, we have the magnetic field is into the page, and the charged particle is positively charged, and it's moving to the right. Whereas on this second problem, the magnetic field is moving upward, and the charged particle is positively charged and moving to the right as well. And then lastly, the charged particle is negatively charged. That's important to know because then that will tell you which direction the force will be going. And then your magnetic field is moving to the left. So if you'd like to pause the video and go ahead and solve these, you can, or the answers are right here. So the answer for the first one, the force will be moving up. The answer for the second one, the force will be out of the page. And for the last problem, the force will also be up. So now we're going to cover an MCAT-like question. So the question says, an MRI uses a magnetic field and radio waves to produce detailed pictures from inside the body. If its magnetic field is 3.0 T, what force does the MRI have on a hydrogen, that should say ion, a hydrogen ion, at rest in the human body? So go ahead, if you'd like to pause the video and try to solve this. Just a hint, you're going to be using the equation for force that we provided earlier, where force is equal to QV times B times the sine of theta. Or below we have the solution. So actually, since the magnetic field it said was 3.0, we're going to have 3.0 T there. So here, like I said, we solved it using the force equation for where QV times B is equal to the force. So since it's a hydrogen ion, we know that it's positively charged, so we can go ahead and plug in the value for for a positively charged proton, essentially. And then we multiply that by the velocity of the charge. So since the charge is at rest, we can go ahead and plug in 0. And then the value for the magnetic field, it said was 3.0 Tesla. And since we can just assume that it's going straight down into the body perpendicularly, so that would be a sine of 90 degrees, which is just 1. So the answer for that, anything times 0 is equal to 1. So the correct answer should have been 0.